Hello everyone, I am Bertrand Rossio from the CE8 in Grenoble, and my presentation today is Determination of Transport Properties of Gas Diffusion Layer for PEMC with geodect. So first, a few words about the principle of PEMC. So you have two sides. There is the anode side where hydrogen comes, and the cathode side where the oxygen comes. And the oxidation reduction of hydrogen and oxygen produces water and also produces displacement of electrons, so this electrical charge can be collected. There is both on both sides, hydrogen and oxygen comes from bipolar plates here, and on both sides they must go through the GDL, the gas diffusion layer, before reaching the catalyst layer. My work is to characterize this part, the gas diffusion layer, which is composed of a carbon substrate, and sometimes we add a MPL, a microporous layer, sandwiched between the carbon substrate and the catalyst layer. And this is how I work to characterize the GDL. So I took GDL sample and I've done images of the sample by X-ray tomography. When I had the 2D image tag, I could import the image tag on Geodeck to obtain the final 3D structure. And with this structure, it was possible to use Flowdict, Diffudict, or Satodict to calculate some properties like permeability, diffusion, tortuosity, or capillary pressure curve. And with these last curves, it was possible to reach the relative permeability and relative diffusion, and also calculate the Poisson distribution. All these properties are gas transport properties, which are really important for GTL because they characterize how the GTL is able to make a gas go through the structure or not. So first, I will talk about how I imported the 2D image tag on Geodeck to reach the final 3D structure. So there is some processing to do on the 2D image tag to clean the images obtained by tomography because there is noise to remove. There is also crop to make to select the region with which we can work, and also correct the brightness. And when we are satisfied with the quality of the images, we can make the segmentation. We can do automatical segmentation like Ozu segmentation, or also select manual segmentation, because we have to separate air pixel from carbon pixel, which has been obtained after the tomography. Even if we made a few cleaning on the 2D images, there is still some noise to be removed on the 3D structure. As we can see here, there's a lot of voxels which are alone and which doesn't take it part into the real structure. So we have to remove this, and for this I used the cleans tool of Geodeck to remove every voxel which were alone. So this is what I obtained when I applied this last cleaning tool, and I have the final structure on which I will be able to make some measurements. So first, let's start with Flowdict and Diffudict use to calculate permeability, diffusion, and tortuosity. Let me explain how the GDL I studied. All the GDL are from the Cygocell company, and in these examples, they are from the 24 series, and the 24 doesn't really mean anything, but the two letters mean something. The first letters always stands for the amount of PTFE on the fiber coating. So when it is a A, it has 0% PTFE. When it is a B, there is 5% PTFE. And when it is, for example, E on 24EA or 24EC, that means the fiber substrate has 30% PTFE. So first letter is for the amount of PTFE, and the second letter stands for the presence or not of an MPL. So when it is a A, there is no MPL, and when it has a C or sometimes a B, that means there is an MPL. So to take an example, the 24BC has a B as the first letter, so it has 5% PTFE, and it has a C of for the second letter, so that means there is also an MPL. This is the different properties I calculated on a different GDL. Some GDL has an MPL and some GDL have different amount of PTFE on the structure. It is interesting to see that when the PTFE increases, there is a diminution of some properties of transport because between 24AA, 24PA, and 24EA, the PTFE amount increasing from 0% to 5% to 30%, and we can see that the porosity is reduced, the diffusion is reduced, also the tortuosity is higher. So this is interesting, and we can already try to link these values and these results to the performance of the GTL when we use a polarization curve to understand if the GTL works well or not. We can link to the real performance with the transport properties calculated with geodict. The transport properties is not the only effect that affects the performance, but it is a piece of the puzzle to understand why some GTL are performant and some others are not. Now we focus on the value of porosities to compare with the literature values. What we can see first is that in the literature there are a lot of values that can be obtained depending on the method which is used. And we can see that the geodict values are in the range of the literature values, so that validates the values of geodict. And we can also notice that comparing to some methods of porosity like mercury intrusion, there is no damage with the geodic method. Now let's see the permeability values. This time we have different values when we compare geodict and the literature. Because on geodict we often have values of around -10 to -11 meter square, values of permeability, whereas in the literature most of the values are around -12 meter square. But the difference is that most of the literature values are obtained with experiments which are made when the GTL is compressed, whereas the structure is used to calculate permeability on geodict is uncompressed. So there is a gap which can be explained by this, but there is still a bit of gap which is not completely filled because some values in literature are around -11, and there is still a bit of gap to be filled, which is unexplained, but maybe that could be the fact that the image used for calculations needs to be treated, and maybe the image treatment is doing some is making the gap between values of uncompressed values of literature and the one we have with geodict. And now we move to see the capillary pressure curves obtained with geodict. This time we here compare two GDLs, the 24PA and the 24BC, and we can see that between the 24BA and the 24BC, the difference is the first one doesn't have MPL and the second one has an MPL. we can see that the maximum amount of saturation is reduced when there is an MPL. So that could mean that the MPL helps to prevent water to flood the entire structure. It is a positive effect on the GDL for its application. And also we can compare the 24BA curve with a literature curve, which is quite close. So this validates the values obtained by geodict, and something to be noticed is the value of capillary pressure curves are easier to obtain via geodict than doing an experiment. Now let's see the relative permeability and relative diffusion. So here is the values of relative permeability with this curve here, which displays the permeability at different points of the capillary pressure curves. So this means that at different point of saturation, the permeability has been calculated, and this is the curve obtained. It is good to know that this kind of curve is very difficult to obtain by experiments, by laboratory experiments. And this is a good way to obtain this kind of values by just using a 3D structure. This is much easier. Here on the right, we see the visualization of the water intrusion into the structure. What you can see is water is displayed uh, all on the structure of the MPL on the above, and this is before entering the carbon substrates. It takes some time and some pressure, and this is explained by the fact that the pixel size of the tomography which has been used was higher than the particle size of the MPL. So this is why the structure of the MPL was there is no at the places where there is no cracks, it is considered as homogeneous structure, and the water and also the gas penetrates only by the large cracks. So there is an assumption made that all water and gases passes only where there is cracks when there is an MPL. And to finish, let's see the pore size distribution. So for getting the pore size distribution, I used the StatUdic module to modelize mercury intrusion capillary pressure curve. And from this data, I applied the Laplace equation to which links the pressure with the radius of pore, and this is how I obtained the pore size distribution. Now I try to compare this method to getting the pore size distribution with what we can have in the literature, and there is here two values of the same two literature articles of the same GDL, which is here on the left, which is 24 BC, and here on this one we can see that the values of the macropores are here around 8 micrometers, which is very close to the values I had with my method of mercury intrusion pressure curve. And the thing which is in common is that here the method used is standard porosimetry, which is a non-destructive method, like was of course the geotic method. Whereas when we compare with a real experiment of mercury intrusion, which is done by these people, here the radius of the pores they obtain is between 20 to 40 micrometers, because here it is in diameter, but it is still much higher, at least 2 times higher than the values obtained with geodict or with a non-destructive method. So that could mean that the non-destructive method is important to not displace the carbon fibers or maybe break the carbon fibers, because when we inject mercury into the structure, it may cause the destruction of the fibers and change the porosity. So to conclude, I used geodic to determine gas transport properties of gas diffusion layer. It helped me obtain some values which are very difficult to obtain by laboratory experiment, and some values could have been validated except for permeability, because uh, calculations have been made on uncompressed GTL, whereas most of the values obtained in the literature are for compressed GTL. And the use of Geodict was quite fast and so reliable way to characterize GTL, and it will help to continue characterize this carbon substrates, which is the Geodict. Thank you.